Hello, hello, good morning. Hello, good morning.
Hello.
Hi, Elidon.
Hi, how are you?
Fine, and you?
Fine, thank you.
Oh. Hi, Rafaela, Heidi, Isabela.
Hi. Hi, teacher.
We are waiting for the more student, okay? Lourdes. Lourdes. Hello, hello, good morning. Good morning. Etepon, Camila. Hi, Camila.
Good morning.
Hola guys, do you hear me? Hello. Hola guys. Good morning.
Hello, guys. Do you hear me? Hello? Hello, guys. Do you hear me? Hello?
Hello, teacher.
Hello, how are you? Welcome, guys. The class going to be starting a couple of minutes. Okay. Welcome, teacher Eldon Daily. Teacher, do you hear me?
Hello, everyone.
Hello, good morning. Okay, I don't know, Roxana, we can start the class right now. What do you think?
Can we start now?
Yes, yes, Elidon.
So, yes,
Yeah.
yeah,
Be
you can
ready
start
to
right
the
now.
hop.
Yeah.
All right. Can you hear me?
Yes.
Yes.
Okay, so today we are going to explain some topics related to the general chemistry, and for the first topic, I would like to share you some information about the isotopes. And as you know, till now we have learned about the atoms, which is a particle, which in that includes subparticles, which are smaller particles, which can stay in the atom. And these subparticles are the electrons and the protons and the neutrons. As I've written here, the electrons are negatively charged particles, the protons are positively charged particles, and the neutrons are neutral. And as we know, in the center of the atoms are neutrons and protons, and around the nucleus are the electrons. So the electrons creates the electronic cloud for our atom. But if we talk about a single atom, we know that the single atom is a neutral particle. And what is that? That the atom is a neutral? It is because the number of electrons is equal to the number of protons, which means the negatively charged particles, electrons, are equal to the positively charged particles. So the overall charge for the atom is 0. And what about the isotopes? If you look carefully at the periodic table, most of the elements in nature exist at different forms related to neutrons in their nucleus. For example, I'm going to give you here some examples of an atom which has different number of neutrons in the nucleus. For example, helium is an element which has the atomic number of 2 and the atomic mass of 4. What does it mean, the number 2 for the helium? It means that the helium has a number of protons equal to 2, and the atomic mass is related to number of protons plus number of neutrons, which are the particles in the center of the atom. And there are two different helium atoms, because the scientists have found that in helium there are 2 protons in the nucleus and 2 neutrons, which makes the atomic mass equal to 4. But this is the helium, the first helium. But there is another helium which has 2 protons in the nucleus, but it has 3 neutrons, which makes the overall mass for our atom, which is equal to 5. So this is the next helium. And what is the difference between these the same kind of atom which makes an helium, an element, but the number of neutrons in them is different? So we can make a conclusion for the isotopes. The isotopes are the atoms of the same element, but the different numbers of neutrons in the nucleus. I'm going to show you a table for example, I'm going to give you the element A, B, C, and D. And here I'm going to give you protons, electrons, and neutrons for each of them. For example, atom E has 8 protons, 7 electrons, and 9 neutrons. The atom B has 7, 7, 9. The C element is 8, 9, 9, and the last one is 8, 8, and 10 neutrons. And the question is, which of these atoms are isotopes? So, as we learned a few minutes ago, we learned that there is the same number of protons, but different number of neutrons. These are the isotopes. For example, let's look first. Let's compare the atom A and the atom C. The atom A has protons, and also the atom C has 8 protons. So we know now from this information that the element A and C are the same atom, which makes the same element. But let's look if they have the different number of neutrons. They have 9 neutrons, 9 neutrons. So we cannot say that they are isotopes. So they are not. I'm going to compare now the element A with element D. The element A has 8 protons, the element D 8 protons, and the number of neutrons is different. So the element A has 9 neutrons and the element D has 10 neutrons. So from this information, we can just think about the differences in neutron number. It has 9 protons and neutrons, and the D has 10 neutrons. So they have the same number of protons, but different number of neutrons. So this information makes them isotopes. What can we take if we take only 1 minute information about this table? Which of these elements is a cation? A cation is that particle where the number of protons is higher than the number of electrons, right? So let's go for the first one. A has 8 protons and 7 electrons, which makes it a cation with a charge +1. So the first one is a cation. What about the B element? The B element has 7 protons and 7 electrons, which makes it a neutral atom. What does it mean? It means that it is not a charged particle. And the C element has 8 protons and 9 electrons. As we know, if the number of electrons is higher than the number of protons, it makes it an ion. Anions are negatively charged particles, so the C element is C-1 charged. And what about the last one, the D element? It has 8 protons and electrons, so the number of electrons and protons is the same, is equal, so the element D is just a neutral atom. It is not a charged particle. One important thing about the mass of the isotopes if you have a periodic table, or if you think about the periodic table, we know some informations for each of the elements. I'm going to give you an example for neon. If you look at the periodic table, neon has two numbers, two most important numbers above this element. It has the number of 10, and here it is 20.2. So the number 10 is the atomic number, which is represented by the S, and this one number here is the atomic mass. But as we talk about the atomic mass is equal to number of neutrons plus number of protons. But as we know, the number of neutrons is a natural number. Also, the proton is a natural number. But if we make them together two natural numbers, it will produce a natural number of A. But in the periodic table, it is not a natural number. It is a rational number, 20.2 grams per mole. What does it mean? It means that the neon exists in nature as an isotopes, different elements, different particles with different number of neutrons, but the same number of atomic number, which is the proton number. So I'm going to show you three isotopes for neon. For example, the first one, neon, has 10 protons, but the mass of it is 20. The second one is neon when the number of protons is 10, but the mass is 21. And the third element, the third atom, is 10 and 22. So these are the isotopes for neon. And what are the number of neutrons for each of them? The number of protons here is 10, and the number of neutrons is 10, which makes the mass, atomic mass, equal to 20. The second one, the number of protons, it's 10, and the number of neutrons is 11. 20 plus 11 makes 21. The third one, the protons is equal to 10, and the number of neutrons is 12. 12 plus 10 makes 22. So these are the three particles for the neon with the same number of protons, but different number of neutrons. And as we know, the atomic mass, which is equal to 20.2, the method that we can calculate the atomic mass for the isotopes, we have we need enough information, extra information. What is the percentage of accuracy for these elements in nature? So the extra informations for these are like this. The first element is 90.9% of the helium. So most of the helium has the mass equal to 20. The neon with the mass of 21 is represented by 0.3%. So this is very rare element. And the third one is 8.8%. How can you find the atomic relative mass or the average mass when we have the masses and the percentages? The formula for the atomic relative mass is like this, and it is very important. Atomic relative mass, it's equal to the mass of the first isotope, which is 20. This would be multiplied with the percentage 90.9. Then we have to divide it by 100 plus the second one, which is the mass is 21, multiplied with the percentage of 0.3, divided by 100%. And the last one, the mass for the last one is 22. So 22 atomic mass would multiplied with 8.8% divided by 100. And if we make a calculation in this one equation, the result would be 20.2 grams per mole. What does it mean? It means that the average atomic mass for the neon is 20.2. So if you go after this lesson to the periodic table, you would see that all the elements in the periodic table has a different atomic mass, which is irrational atomic number, which is represented by the isotopes which exists in nature. Another information that I would like to share you in this lesson about the isotopes, some of the isotopes which has in nucleus a lot of neutrons, some atoms or isotopes which in nucleus has a lot of neutrons, they are called radioactive elements or radioactive atoms. Maybe you have before coming here in this lesson, maybe you have seen in TV shows on YouTube or etc. Maybe you have seen about nuclear weapons or uranium or atomic war, etc. All of these words, news, and bad stuffs are about radioactive elements or radioactive atoms. These radioactive atoms has in nucleus a lot of electrons, which means with the time they decay. They decay, which means by the time they will separate in some more particles, which would cause an explosion, which would cause, for example, a chain of reactions which happens during the time. I'm going to give you the example of uranium. The uranium is an atom which is radioactive. And the uranium has the atomic mass of atomic number of 92, and the isotope is 272. What does it mean, this huge number? It means that 92 is the number of protons, 92 is the number of electrons, and 272 minus 92, which would be equal to 180. This is the number of neutrons. If we compare the number of protons with the number of neutrons, the number of neutrons is very high. It is a huge number. And this huge number of neutrons in the center of the uranium atom makes it very radioactive. And by the time the uranium will decompose in another atom, for example, plutonium, and for example, this is an element, another element, and plus 3 neutron particles. These neutron particles are very dangerous, for example, if we use uranium for the atomic bombs. And these neutrons will go to another uranium atom, and this uranium atom would explode to another atom plus 3 more neutrons. So this reaction never stops. It will go further and further. But the scientists have found that the radioactive elements or radioactive atoms can be used in medicine as X-rays. We can use radioactive to calculate the age of mummies or the age of old trees. So it is useless if you use it for bad stuffs, but if we use it for good things, to know the age of different bodies, bones, or trees, it will be great to use it. Okay, that's it about the isotopes and radioactive elements. Another topic that I would like to share, the topic would be about molecules. The molecules, as we know, is made by combination of non-metallic elements. I will give you an example. For example, hydrogen has the atomic number of 1, which makes hydrogen an element which has in the center 1 proton and 1 electron. But this element, like this, as I have written here, is unstable. It is unstable because it needs to complete the outer shell. What does it mean to complete the outer shell? It means that it will go and search for another element like himself or another elements to complete the outer shell. Sometimes elements gain or give some electrons, but when we talk about non-metallic atoms, they would share electrons. So what does it mean to share electrons between non-metallic elements? Our hydrogen will go and search for another hydrogen, which I'm going to represent it with the blue color, which also has 1 proton, the atomic number of 1. So 1 proton in the nucleus and 1 electron in the outer shell. So they will meet each other like this. So this is our atom, the second one, and this is the first one. So their electronic clouds are merged together, and each of the electrons stay in the center of the molecule. So this one, which I've written here, is called a molecule, where 2 electrons has been shared. Or we are going to call it a pair of electrons. And we are going to call it a covalent bond. So two atoms of hydrogen now are together, then they have formed a molecule of hydrogen, H2. So hydrogen exists as a diatomic molecule. So there are 2 atoms in the same molecule. So we have hydrogen as this. So from now, you should know that the hydrogen cannot exist as an atom, but it can exist as a molecule, as H2. Another thing about molecules, the molecules can be a combination of the same element or the same atomic elements, but also it can be formed by different atomic non-metallic elements. The most famous, which we use every day, is water. So the water is a molecule, and each of molecules is represented by a formula. And the formula shows the smallest ratio of the atoms which combine with each other, and they all of them complete the outer shell with electrons in order to have a stable arrangement of outer shell electrons. So the water is represented by the formula H2O. It means that the number 2 represents the number of hydrogen atoms in water, and O is for only single atom of oxygen. The atomic number for oxygen is 6, and for the hydrogen, the atomic number for hydrogen is 1. It means that oxygen needs, the atomic number for the oxygen is 8. So oxygen needs 2 more electrons to complete the outer shell, and the hydrogen also needs 1 electron. And the molecule of water exists like this. So oxygen has formed 2 single covalent bonds, with 2 different atoms of hydrogen. So this is the smallest ratio of combination between hydrogen and oxygen, which would form water molecule. Another molecules that are famous in our everyday is carbon dioxide. Carbon dioxide is a molecule because it is a combination of non-metallic atoms, carbon and oxygen. In this example, we have 2 atoms of oxygen and 1 atom of carbon. And we are going to talk later about the formation of the bonds between them. But in this lesson, there is not enough time to explain all the bonds formed between them. It would need more time. I'm going to share also some of the famous molecules. It is oxygen. Oxygen is an element that we breathe in, and it is formed by 2 oxygen atoms between them. The oxygen, as I told, has 8 electrons, and it needs 2 electrons to complete the outer shell. So it will fight every day to find these 2 electrons. Sometimes it finds these electrons with metals, but sometimes it finds these electrons with non-metals, and sometimes by himself. And for the oxygen, we have 8 protons in the nucleus, 2 electrons in the first shell, and other 6 electrons are in the second shell. So it needs 2 more electrons to complete the outer shell with 8 electrons. And also another oxygen would come here, will meet him, and they would share electrons between them. But sharing electrons, it's not as simple with hydrogen, where they shared only 1 electron each of them. In this case, oxygen needs 2 electrons, so oxygen would give 2 electrons to another oxygen, and another oxygen would give 2 electrons to it. So they would have a great relationship between them. They would form a molecule where 2 of them are happy and 2 of them has 8 electrons in the outer shell. How to understand this? Let's draw this combination of these oxygens. Here is the first oxygen. I'm going to draw here only the outer shell for the oxygen. And here comes the other oxygen. Here is the nucleus, which is positive, and here is the nucleus. The electrons for the first oxygen would share 2 electrons because it needs 2 electrons to take in. So it would give 2 electrons to be in order. And another oxygen also would share 2 electrons So the combination of them would be very interesting. I'm going to draw only 6 electrons for the right side of oxygen. So till now I have drawn here 2 of 6 electrons of the outer shell, 2 of them, and here are 2 more, and here are 2 more. So here I have driven 6 electrons in blue, which makes the outer shell for the left side, for the right side of oxygen. In the left side is oxygen also with 6 electrons. Here we have 6 in red of electrons of the oxygen in the left and 6 for the right. But if you look carefully, in between them there are 4 electrons, 4 in the middle and 4 out. It makes that this atom of oxygen has 8 electrons in the outer shell. Also, the right side has 8 electrons in the outer shell. So both of them now are happy. And if you look carefully, there are 4 electrons between them. 4 electrons means 4 electrons which has been shared. Or we can just write it as pair of electrons. So there are 2 pairs of electrons, which means, in other words, there are formed a double bond. A double bond is represented like this, or we can write it oxygen, double bond, and oxygen. So this is the oxygen as a molecule. So from this lesson, you would think about oxygen that we breathe in every day. It is not like simple O2. It is oxygen double bond oxygen. So there is a reaction. There is a chemical change that forms a molecule. There is a combination of 2 oxygen atoms in one single molecule. I have some extra molecules which are bigger and different from the previous molecules. For example, H2CO3, which is carbonate or carbonic acid. This is the acid that we drink a lot today with our juices. For example, Coca-Cola or Pepsi, etc., contains a lot of carbonic acid, and this is a molecule. This is a molecule when in this we have 2 hydrogen atoms. We have 1 carbon atom, and we have 3 oxygen atoms. All of them are non-metallic elements, and they has formed a molecule by the combination of them. There are some single and double bonds between them. I'm going to show shortly like this. This is the carbonate group CO3, which is 2 negatively charged, and here are 2 hydrogens, which are positively. They make a combination, they make a covalent bond between them, and they form a molecule. Another example would be ammonium nitrate. Also, this one is a molecule, but be careful, in this molecule, we have same element, which is nitrogen, but it stays with ammonium group and with nitrate group. So if I would ask you a question, how many nitrogen atoms we have in this molecule, there would be 2 nitrogen atoms. There would be 4 hydrogen atoms and 3 oxygen atoms. So this is the smallest the smallest ratio of combination between the elements to form this molecule. If there is less one nitrogen atom, that molecules that would not exist because there are needed some electrons to complete the outer shell for the other elements like this. Another element, or sorry, molecule would be a combination of carbon and hydrogens. Here are the bonds which are formed between carbon, hydrogen, carbon, carbon, and this is a thing. This is a gas that we use for cooking or for heating. So here we have 2 carbon atoms and we have 6 hydrogen atoms. This is the combination between carbon and hydrogen. Another thing would share with you would be a triple bond which exists in some elements. The most famous one is nitrogen. So as we know, nitrogen has the atomic number of 7, and which means that the nitrogen has 7 protons in the nucleus. It will have 2 electrons in the first shell and 5 electrons in the second shell. So as we talked about before, if this element has 5 electrons in the outer shell, it would need more electrons to make 8 electrons. So it's simple that it needs 3 electrons to make 8. So how can nitrogen find these 3 electrons? It would search for another elements like carbon, like nitrogen, to complete the outer shell. Let's draw another atom for nitrogen, which is the same conditions. 2 electrons in the first shell and 5 in the second shell. And just think about this. If you need 3 electrons, if you are a non-metal and you need 3 electrons, you would share 3 electrons in order to gain 3 electrons. So there will be 6 electrons in the middle, or 3 pairs of electrons. For example, let's draw now the molecule of nitrogen. Here, the nitrogen in the right would share 3 of its electrons, and it would stay only 2 electrons, which are personal electrons in the right. And in the left, also, it would do the same thing. It would share 3 electrons, and 2 of electrons are personal electrons. As we can see, it's clear that there are 6 shared electrons, which makes 3 pairs of electrons, and in chemical nomenclature, it means it is a triple bond. A triple bond is represented by 3 pairs of electrons or 6 shared of electrons. So if we draw this formula simply, it will be like this. This is the element which is the most abundant element in the atmosphere, with a percentage of 78, and it's written like this, N2. This is a molecule. It is not an atom. It is the free element of nitrogen, but just N is atom and N2 is molecule. Be careful, remember the difference between molecules and atoms. That would be the differences between atoms and molecules. Okay. Another topic that I would like to share with you is electronic shells. Okay, so the electronic shells are some places in the electronic cloud which are around the nucleus of an atom, given atom, where the electrons move around. They move like the planets around of our sun. So what are the rules that we should know about the electrons in some given atoms? We should know that the shells will be represented by n number. So the n number, which represents the shells, would be from 1, it can be 2, 3, 4, 5, 6, and 7. So the maximum for the shells for given atoms, different atoms, would be, the maximum is 7, and it starts from the first one. But the electrons which move around this from this one have different energies. So some electrons are closer to the nucleus, some electrons are far away from the nucleus. And what is the difference between electrons? The particle is the same, the charge for the particle is the same, and the mass for the particle of electron is the same. What changes between them is just the position of movement, the distance of this electron from the nucleus of the atom. I'm going to show you the hydrogen and the lithium. The hydrogen has the atomic mass of an atomic number equal to 1, and lithium the atomic number of 3. And we should know some information if we want to draw the shells for these atoms. The information that I would like to share with you is, if the number of shell is 1, the electrons, the maximum of electrons that can have a position at the first shell, it's equal to 2 electrons. If the shell is equal to 2, so if the atom has only 2 shells, the maximum of electrons that can have the position of the second shell is 8 electrons. If the shell is equal to 3, the maximum of the electrons is 18 electrons. And the shell is equal to 4, there can have a position of electrons will be 32 electrons. So this is one of the shells when the maximum for the electrons is 32. If n is equal to 5, also there can have the place 32 electrons. The the shell equal to 6 would have 18 electrons, and the shell which is equal to 7, the last shell for some elements, there will be only 8 electrons. So if you remember this table, it will be great, and we can work on again like this for remembering the number of electrons in different shells. For example, you can just remember it like this. 4 is equal with 5, 6 is equal with 3, and 7 is equal with 2. Only the first one can have 2 electrons, and the other shells can have different number of electrons. But also in these shells there are some subshells. The subshells are some smaller electronic levels where these electrons, which have the position of different shells, can have just a tiny change of the distance between them related to the nucleus. It starts with the first shell to the last one. For example, I'm going to represent you the atomic configuration of the electrons for the hydrogen. So the atomic number of 1 means that it has 1 proton and 1 electron. So 1 proton is in the nucleus. This is the first shell, and here is the electron which moves around the nucleus, like the Earth with the sun. The lithium has the atomic number of 3. What does it mean? It means that it has 3 protons in the nucleus. The first shell, as we said, can be completed only by 2 electrons. So here are 2 electrons in the first shell, but lithium has 3 electrons. Where is the third electron located? It cannot be at the first shell because the first shell is completed. So we have to draw the second shell. And the second shell here is the third electron, which is in this position. So this is a configuration for the lithium atom. 2 electrons in the first one and 1 electron in the second shell. We can write it like this: 2, 1. So here, this is a configuration for the electrons for the lithium. Let's go and work with another element which has a greater number of electrons. I would share phosphorus. The phosphorus has the atomic number of 15. So this is more difficult to remember, but if we look carefully at my table that I gave you, you can easily draw it. So 15 protons in the center, and then I'm going to draw the first shell where are 2 electrons, but the first shell can have only 2. The second shell can have 8 electrons. So I'm going to draw here 8 of them. It is a rule that we have to draw the electrons in pairs. So from this moment, I have written here 2 plus 8, 10 electrons. We need 5 more electrons to draw. So I'm going to the third shell. Here is the third shell, and here, as we see, it can have 18 electrons, but we need only 5. Here, there are 2 pairs of electrons and 1 single electron in this position. So how can we write it differently? Would be like this. It's 2, 8, and 5. This is the configuration of electrons in phosphorus atom. And what can we have? For what do we need this drawing stuffs and configurations? For coming lessons, we would need them to understand why do they act differently in different reactions, in different combinations to form molecules. I'm going to tell you that the most important thing about this is how many electrons do they have in the outer shell. The outer shell is that makes the differences between the elements. For example, the phosphorus has 5 electrons in the outer shell. The lithium has 1 electron in the outer shell, and the hydrogen has only 1. So they would act differently between them in order of this number of electrons in their outer shell. For example, the metals generally they give out electrons, and the non-metals gain in electrons to complete their outer shell. And about the sublevels, it would need more time to explain it, but the sublevels are some positions in the electronic cloud when the electrons move around with differences in energies, because some of them do not have a lot of energy to stay in the same position with other electrons, so they would move a little bit far away from the nucleus, and to have the position always to not change their energies. The sublevels are S, P, D, and F. These are the sublevels, and their energies are different. And the electrons that can have the positions here are in the sublevel S. There are only 2 electrons that can stay in the single sublevel. In the sublevel P, there is a maximum of electrons which have this position. In the D sublevel, there are 10 electrons. And in F position, sublevel, which is normally for the elements which are radioactive or artificial elements found by different scientists like Marie Curie, etc. And this sublevel can have only 14 electrons. But that would need more time to explain, of course, because a lot of information can be given for other lessons. I think that's it. If you have a question about these topics, I would like to answer you. Can you hear me?
Yeah.
Professor Ilidon, what is your question? Sorry.
Does any one of you of the students have a question?
Guys, do you question for the teacher, please? Nothing? All is good?
No.
It's okay, Professor. It's okay. A ver. One moment, please.
Continue, teacher. Everything is clear.
Thank you. Can I ask a question for some of the students?
Yes, no, everything is clear, but let's continue and we're going to close the class. Okay. Let's continue, teacher. Everything is clear for the student.
Can you repeat that?
Let's continue. Everything is clear for the student. Do you hear me?
Yeah.
Yeah, you can continue. Everything is clear, and when you're going to close the class, let me know, okay?
All right.
Okay, thank you.
Okay, bye.
Thank you, guys.